Hello everyone, and welcome to my presentation of the comparison of deep learning and knowledge-based approaches to predict pedestrian trajectories. My name is Raphael Korbmacher. I'm a PhD student at the University of Wuppertal, and I did this work together with my supervisor, Professor Antoine Tourdeau, also from the University of Wuppertal. First of all, the motivation of this article is that the deep learning algorithms are really a hot topic for the prediction of pedestrian trajectory recently. As you can see in the diagrams, for example, here with the social LSTM from Alahi, which gained a lot of attention in the last years, you can see how much influence these kind of approaches have in the pedestrian dynamics. On this diagram, for example, we did a Google Scholar search where we looked for requests for social force associated with pedestrian dynamics and associated with pedestrian and human trajectories here. And also we did a request for neural networks associated with pedestrian or human trajectories and for neural networks associated with pedestrian dynamics. You can see most of all neural networks are associated with pedestrian trajectories, whereas social force is associated with pedestrian dynamics. And you can also see that the neural networks gained a lot of attention. Reasons for that are that the predictions are really useful for many real-world applications, and that the deep learning algorithms in the neural networks have shown to be highly accurate in the predictions, or even better than the knowledge-based models, like, for example, the social force model from Helbing. And at least there are also many data available recently, which makes this topic more relevant. Okay, so now what are the knowledge-based approaches? These are mathematical models that are also sometimes referred to as physics-based, reasoning-based, expert-based, or traditional approach. They are defined by basic rules or generic functions and consider physical as well as social or psychological factors in the equations. Important characteristics are that these models have just a few parameters that can be interpreted, like, for example, the desired velocity or the vision angle, that predictions of the trajectories are done via a forward simulation. So you have a situation and you make a simulation based on your equations so that you can predict future trajectories. Famous classes of the knowledge-based approach are the acceleration-based models, the velocity-based models, or the cellular automata models. Applications are, for example, in evacuation situations or in infrastructure design. And here are some famous articles, for example, from Helbing or Burgstede or Vandenberg. Deep learning approach. This approach is also often referred to as data-based approach, learning-based approach, or pattern-based approach. It is based on algorithms that learn past trajectories to predict future trajectories. Important characteristics are that the algorithms are not validated or not calibrated, but they are trained on data. They learn patterns in the data, which they use to predict future trajectories. And three important classes that have to be distinguished are the long short-term memory networks, the convolutional neural networks, and the generative adversarial networks, also called GAN. Applications are, for example, in autonomous vehicles, where the vehicle have to predict future behavior of the pedestrians in the vision angle, or social aware robots. Famous articles are, for example, the social LSTM from Alahi, the social GAN from Gupta. Here is a CNN model from G, and these are also important articles. Now, let's get to the comparison of the two approaches. First of all, we have a technical approach comparison. Here you can see semantics are different. When you have the knowledge-based approach, you talk about models with parameters, whereas the deep learning approach are based on algorithms with coefficients. These algorithms have to be trained and tested, whereas in the knowledge-based models, you have to calibrate the model and validate it. Yeah, also the methodology is different because for the knowledge-based models, you have differential equations or cellular automata models, and deep learning is mostly neural networks, for example, LSTM, CNN, and JAMP. Interesting are also the differences in the inputs. When you make predictions with knowledge-based models, you use the actual state of the system. For example, the pedestrian position, the relative position between the pedestrians, or the velocity of the pedestrians. In the deep learning approach, you have path trajectories you use for the predictions, not just the actual state, but the path trajectories. And then there are also differences in the output, because here the output are just small time steps, like for example, from just a millisecond, but in the deep learning approach, you have greater time steps, for example, 3 to 5 seconds. We also want to emphasize some modeling concepts, some differences in the modeling concepts. For example, knowledge-based models are associated with the fundamental diagram, with desired velocity and social force, with floor fields or collision avoidance. But deep learning algorithms, they are often focused on human interactions, on social pooling, on attention mechanisms, on group dynamics, and human space interactions. And the performance are evaluated different. For the knowledge-based models, you have flow density relationship or compared to experimental data, whereas deep learning there you have some key figures, like for example, the average displacement error or the final displacement error that you use to evaluate the performance of your algorithm. Furthermore, we have done an application-oriented comparison. For the application, also the applications are different. As you can see in this table, the knowledge-based models are used as a simulation tool, are used to check infrastructure designs or to plan infrastructure design for evacuation situations and for intelligent transport systems. The deep learning approach is often used for, as I said, autonomous vehicles, social aware mobile robots, for design of intelligent tracking systems. Yeah, and also an important difference is the application scale, the differences in the application scale. Knowledge-based models are used for large-scale simulations, for example, for infrastructures like train stations, stadiums, or malls. But the deep learning approach often focused on just a few pedestrians who are interacting in a local scale with local pedestrian scale in time and space. And this also is important for the crowd density because deep learning approaches are mostly used in low density situations with just long range prediction interactions, whereas the knowledge-based models are used for both. They can be used for high density situations where you have crowds of pedestrian or for low density situations. Advantages of these models, of the knowledge-based models, are that they have interpretable parameters, that they make predictions which can be reproduced and are explainable because you know why the decision or the prediction is made, and there's not so much dependence on data. Disadvantages are that they only model average behavior, that they are not suitable for complex interactions and can't cope with a whole range of different behaviors in a single model. Advantages from deep learning approach are that they make accurate predictions, that they learn complex interactions, and there's no knowledge needed, just data. But disadvantages are that they are not interpretable, the parameters are not interpretable and not reproducible. So you don't know why the prediction is made this way, why your algorithm to this decision. Also, there is a lack of generalization. You don't know if you trained the network on one pedestrian situation, it is not clear if this algorithm is also performing accurate in different pedestrian situations the network was not trained on. Yeah, and the necessary complexity of the network is a priori not known, so you just have to try different settings for a network. These two figures should emphasize the differences of the applications. On the left side, you have low density of pedestrians in a small situation where there are long ranges between the interactions of the pedestrian. Here, the neural net, the deep learning algorithms have shown good accuracy in the predictions of the pedestrian. On the other side here, you have crowds of pedestrians. Many pedestrians in high density with many interactions and crowd behavior. And for these situations, neural networks have not shown yet to be accurate. But here, knowledge-based models are good because in simulation platforms, you can try to use them and they show high accuracies. Now we come to the future directions of pedestrian predictions. We think that a hybrid approach could be promising. In the hybrid approach, you use your knowledge-based models and you use data and algorithms. There are many different ways how you can combine both approaches. For example, with data generation. You use the knowledge-based models, make simulations to get synthetic data, and these data you use to train a neural network. So you have the advantage that you have more data and you can simulate different situations for which you can train your network. This is one possibility of the hybrid approach. Another possibility would be knowledge-guided design of architecture. For example, Antonucci embedded the social force model in the neural network to use the knowledge we have about pedestrian behavior for the neural networks. Other possibilities are the residual modeling, where, for example, neural networks learn to predict the residuals of the knowledge-based models and improve the predictions of the knowledge-based models by learning the residuals. Knowledge-guided initialization of the network is a possibility, and more possibilities are given in these reviews. Other directions we see are to implement neural networks in simulation platforms, because right now, simulation platforms are mostly based on knowledge-based models and equations, for example, the social force model. Here, neural networks can be used to improve the simulation platforms. Also, not yet known is how good neural networks are for high-density situations, because they are mostly applied for low-density situations, as shown before. And another open question is how other inputs than trajectories are useful for the neural networks. For example, maybe the time to collision is a variable that can be used to improve neural networks. Thank you very much for your attention.